Welcome back. We'll be talking about chapter 9 today. Chapter 9 on the ACI 318-14 is about beams. It's a pretty exhaustive chapter. We'll not be talking about every little detail, but the idea is to cover topics related to a PE exam and topics related to SC level breadth exam. Okay, we're not talking about SC level depth. Um, if we have to do SC level depth, then we'll have to spend quite some time on all these sections. Okay. Now the idea behind making this video, um, all these codes, mainly ACI and many structural codes for that matter, are very heavy on text but light on visuals. So my goal is to take these dense, complex clauses and bridge the gap with simple hand-drawn sketches. You'll be seeing multiple sketches that I'll be drawing. Most of them are not crisp, or they're not up to the mark, but they just serve the purpose, right? And that's why I call them chicken scratches. But idea is we will go through the code and do those chicken scratches and directly on the code canvas. I'm trying to transform all these abstract rules into clear mental images if possible. This visual association makes it much easier for you to recall specific requirements when you are under pressure, like under exam setting. So in this video, we are breaking down chapter number 9, and we'll not be covering everything. What we'll be covering would be, we'll be talking about mainly about beams, and then we'll be talking about the shear, flexure, and shear, right? We'll be talking about multiple topics, stuff like minimum, what is the minimum depth required of a beam, right? We'll be talking about how do you calculate your factor moment and shear. How do you calculate your sectional strength? You given a certain B, a certain D, a certain reinforcement. How do you calculate its um, design capacity? How do you calculate the nominal, and how do you calculate design? We'll be spending a decent amount of time on this particular factor here. It is called strength reduction factor. Um, it depends upon the level of strain, mainly for beams under flexure. It depends upon the level of strain of the steel reinforcement. So we'll be covering things like that, right? And then we'll also look at some area of steel, minimum area of steel requirement. We'll also look at some minimum shear reinforcement requirement, right? And then we'll also look at critical sections where I mean, how do you decide where the critical section for shear is and things like that, right? What we will not cover is we will not cover anything about torsion. We will not cover anything about pre-stressed concrete, right? There are a bunch of sections you will see me skipping, but that is intentional because again, like I said, the intention is to cater to the PE breadth level and SC breadth level topics. So we don't want to get into every little detail. So you'll see me skip a bunch of tension, pre-stressed concrete, and you'll also see me skipping up through reinforcement detailing. Okay, because this itself will take a nice session. We'll do it, but then we are not doing it right now. Okay, so you will get little bit conversant with this section, and I also intend to do 6 to 7 problems on flexure and shear. Okay, this will be nice problems wherein we'll try to find out the flexural capacity of a key beam, flexural capacity of a single reinforced, or a doubly reinforced. We'll talk about how do you calculate the shear capacity of concrete, shear capacity of steel, combined shear capacity, and then we'll do some practical problems. Okay, so that's the goal of this video. So let's get started. Like I said, chapter 9. Chapter 9 starts from page 131. I don't have a bookmark copy. Uh, Okay, so this is chapter 9. It caters to these three things. It talks about composite beams, of concrete elements constructed in separate placements but connected so that all elements resist the load as a unit. So maybe you're doing a beam, and then later on you're coming and doing a slab, right? And these two things, a beam and slab, are I mean, after the slab is dry, it acts as a composite T section. Okay, so it caters to um, sections like this. It also caters to simple sections like that. It also caters to one-way joist systems, right? We'll talk about that. And then deep beams, according to so maybe there is a beam, but it's a deep beam, right? So that's what this chapter is gonna cover. It's pretty simple. If you are looking at properties of concrete, then you should go to that chapter. Properties of steel used in beam, then we will have to go to this chapter here. If you're talking about material requirement, detailing requirement, then you go to chapter 20, right? Um, so basic stuff like that. Okay. Um, We'll also talk about T-beam. T-beam is when you have a, like I said, like I drew it in the previous sketch. You cast a slab first. Sorry, you cast a beam first and later on put a slab on it. Not the entire slab will act as a beam. There's a portion of the slab that will act as a work with the beam together, and we'll see how we can find the effective flange width and all that. But this chapter also covers T-beams. Okay. We will not do torsion, so this section here is about torsion. We're not going to do that. Our first interesting section is this section here. This is about the minimum depth of a beam required. You have a nice table here. You need to, whenever you have a table, you need to see if you fall here, 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 or there, and then find out your minimum depth required. So simply supported beam. The L here is, let's say you have a simply supported beam. That's the most important thing, which is not given anywhere here, right? If you have a simply supported beam like that, L is not this clear length. It is from the center of the support, that is your L. So given that L of a simply supported beam, and I mean, given the fact that it is a simply supported beam, and given the value of L, you can calculate your minimum depth of the beam required. This will serve as a starting point for you. Then you can start designing the beam and see, do all the checks. Minimum depth required is that much. Now you can violate the minimum depth required, but then you will have to compute the displacements and show that the displacements are within the limit, like in the slab story. So this is just a recommendation, um, and serves as a very good starting point for a beam design problem. Okay. Now this table holds good for Fy is equal to, if your Fy is 60 10 cube psi, right? But if your Fy is different, if something other than 60,000 psa, then you have to multiply these values with this factor here. This is just a factor 0.4 plus your actual Fy by 100,000. Okay, so if you're using 80,000 psi steel, then you substitute that factor, find this value, multiply these two things with that factor to calculate your minimum depth required. So that's a pretty important minimum depth required table there. Okay. Now we are not doing pre-stress concrete in this session, but then there's some guidelines for the pre-stress concrete depth calculation, and you will have to again multiply these values with some other factor, and that factor is here. Okay. This is not. Let's talk about this section here. So strength of these beams, right? How do you find the strength value? Strength required shall be calculated in accordance to the factor load combination. Obviously, you have loads and your load cases. You're not designing the section for the load cases. You're designing it for the load combination. So suppose you have a dead load and a live load, and you are designing it using the LRFD philosophy. Then you do 1.2 dead plus 1.6 live. Calculate that is your ultimate load, and based on that ultimate load, maybe it is a simply supported beam and you have an ultimate load, so you calculate your bending ultimate mu ultimate moment as WL square by 8, right? So you can calculate, if the end conditions are different, then you calculate it differently, but then that is what I mean, you have to get your you have to you size the section based on the load combinations and not the load cases, right? Required strength, how strong is the beam, you have to calculate it in accordance to this particular section. We'll get into all those details, right? So that is about chapter 6 is about structural analysis. Now how do you get how do you capture your, I mean, you how do you calculate your factored moments? You get the factored moments from the factored loads. How do you get the factored loads? You have a dead load, let's say 100 psf. You have a live load, let's say 100 psf. Then you get a factored load, which is 1.2 dead plus 1 point, let's say 1.6 live. From this factored load, you get a factored moment, right? That is how you capture calculate a factored moment. You calculate factored moment, and you can also calculate your factored shear values. Now you size your section for these things, size and do all the other checks for these factored loads. Pretty straightforward, um, nothing super interesting. So this is one interesting section wherein um, when you have a beam, like that, and let's say it is simply supported, and you want to design it for shear, right? So you don't, let's say this is the, here is the center line, here is the center line, here is the center line, right? And there is a UDL there, let's say W. Okay, center line to center, so let's say the L, correct? So you don't design, you try to idealize from this, you try to idealize and then come up with some diagram like this, right? So this is A, this is RA, this is RB, and this is your W. So RA is equal to WL by 2, RB is equal to WL by 2, but you don't design the beam for WL by 2 for this particular, in this particular case. You design it for a shear which is at a section called a critical section. Okay, so this is, let's say, let's call this critical section, section 1 1, and this section is talking about where that critical section has to occur. So for example, a simply supported beam, and it is a non-pre-stressed beam, we are not talking about pre-stressed, non-pre-stressed, then it happens at a section D. D is the effective depth of the beam, right? Let's say here is the reinforcement, D is effective depth, and this critical section happens at a distance D from the face of the support. So that's the face of the support. Here it is, and the reason there is, let's say you're standing here, then your weight your weight is not getting transformed into shear directly. Gets transformed into compression and goes directly into the support. Whereas if you're standing away from the critical section, then all your weight is translated in the form of shear at that particular section. So you design, so that's why there is a critical section, and we'll talk about different scenarios here, but then I want you to notice the word called critical section, which is located at a section D from the face of a support for a non-pre-stressed um, beam. Okay. Now that's a nice picture here. For example, if you are here in this scenario, here is a T-beam. This looks like this is the top flange of the T-beam, and you have a load, and it is simply supported. So your critical section is at a section at a distance D from the face of the support. If you are here, it is a, here there is a column beam and beam connection, right? So from straightforward, critical section is that section which is at D from the face of the support. This is an interesting thing, and we skipped a little bit of text there, but then this image is pretty easy to digest than reading the text and then trying to understand it. So in this case, for example, when there was a load here, that load was producing compression in the section here, right? That is when the critical section will be at section D. But there are scenarios wherein, think about this beam here, wherein there is a load, let's say this is the UDL acting on it, right? And that UDL is causing tension in the support here, correct? So when the loading causes tension in the support like that, that is when you take the critical section not at D from the face of the support, but at the face of the support. So when you try to design this beam, your shear should be calculated at that location and not D from the face of the support. Okay. There's another scenario wherein, let us say you have loading within the D distance here. right? This is D from face of the support, but then you have a load within the distance D. Then again you calculate you treat your critical section to be the face of the support. That would be your critical section. So that is what is given in this section here. If you read it when you get a chance, but then that is what uh, the whole thing is about. Okay, we're not talking about torsion. Uh, design strength, this should be pretty familiar by now. You take your nominal strength, you reduce it with a factor, and you compare that with your ultimate moment. This is from the loads that you are applying, right? From wind, from dead, from live, from earthquake, from snow, from roof live load, and all that. That's you calculate your mu, and then you compare it with you calculate your nominal strength, but reduce it and then design. Correct. The same thing applies for. So this is for bending, this is for shear, this is for torsion, this is for axial force. But the concept is all the same. Okay. The idea of today's session is to find out how I can calculate my mu, how I can calculate my vu, how can I calculate my fee, right? So if I have those, then I know how to calculate my demand, correct? But how do I calculate my nominal? Sorry, these are all nominals. How do I calculate nominal? How do I calculate my strength reduction factor? Now, strength reduction factor can be for bending, for shear, for tension, for axial compression, for torsion, and all that, right? So we'll go through all those details. Okay. Now let's talk about let's talk about the strength reduction factor. It is in section. So we're currently at page 136. We'll come back to 136, but let's go to this particular section here, and this is about strength reduction factors. So here is a nice table, strength reduction factors. Now let's say this is my favorite line. If they give you a table, you need to find out which row you fall, which column you fall. Correct. If you are dealing with moments, axial forces, or combined moment and axial forces, then you are between that range. So this table doesn't give you the exact value. Let's say I'm talking about moment. What is my number for my strength reduction factor? You will have to go further. You'll have to dig a little bit deeper. But then here, this is just a range. So when you have moment, axial force, or combined moment and axial force, then you are within that range. When you have shear, your value is 0.75. Now you can, in an exam setting, you cannot go back and forth and keep on looking at these values. You will have to memorize all this. Usually for bending, if a certain condition is satisfied, your strength reduction factor is 0.9. Not always the case, but then we'll look into those details. Strength reduction factor when it comes to shear is 7.5, right? Strength reduction factor when torsion is also roughly 0.75, bearing 0.65, and column compression. You have a column and you're subjecting the column to compression. You find your nominal force, nominal strength, and you multiply with the strength reduction factor, and that is usually 0.65. The reason that is column will can be subjected to buckling, and it's more crucial. So we reduce the strength by a much larger factor than what we do for bending and then shear. Okay. Anyway, in short, you have a table here, strength reduction factor, and depending on what scenario, you can pick up. Most of the times, it is pretty straightforward when it comes to picking up the strength reduction factor. Okay. So that is strength reduction factor. This is the most important page when it comes to beam design. If you have to do anything with beams, if you want to solve any problem on beams, be it flexure, finding the flexural capacity, or finding the shear capacity, you need to understand this particular table here. Okay. Um, so there are different zones in this table. One is called, I think the most easiest way to explain is looking at this diagram here, right? There is this zone. So firstly, the x-axis is the strain in steel, right? That means, let's say you have a beam and you have reinforcement, and you are subjecting this beam to, let's say this is a beam sitting like that, right? And you are pushing it UDL. The beam is trying to bend like that, correct? So there is a tension at the bottom, compression at the top, and we are talking about the steel, the strain in the tension steel. Okay, so we have to so x-axis is about the strain in tension steel, y-axis is your actual phi factor. Okay, now you can pick a phi factor if you know the strain in your steel, if you know the exact value. Okay, so if your strain value falls here, then you will have to pick up a phi factor based on um, um, that envelope there. Okay, but if you have spiral reinforcement, you will go a little further and pick up your phi factor. If your thing falls here, if your strain, we'll see how to calculate strain and all that, but if your strain falls here, pretty straightforward, you either pick from here or pick from here depending upon the reinforcement. If you have spiral reinforcement, you go to the dotted line. If you don't have spiral reinforcement and you just have regular ties or hoops, then you are going to stick with this line here. Okay, now there are different zones. First zone is firstly for a beam. Let's say I have a beam and I provide a certain amount of reinforcement, right, and I subject it to a certain amount of load. So based on the geometry and all that, you can find out what your strain in steel is. If the strain in steel that you calculated, we'll see how it can be calculated, but for now let's assume that your strain in steel is 0.003. Okay, so firstly, if the strain in steel is less than a 0.004, then it is not even legal. So this is an illegal beam. Okay, this is not allowed by the code. If your strain in steel is less than 0.004, code only encourages beams wherein the strain in steel is greater than or equal to 0.004. So if you designed a beam and you found out that it is less than 0.003, then you are not allowed to use that beam in practice. Okay. Um, so what happens is for let's talk about let us assume that this is a 60 psi steel. Okay, so for 60 psi steel, you divide that with Young's modulus, which is 29 into 10 power 6, then you get 0.002, and that is your epsilon steel at yield. Okay, and that is this value here. So for a 60 ksi 60 10 cube 60 ksi steel, this value is 0.002. Okay, if it's some other steel, then this particular limit will shift to the right or left. Okay, but for this particular 6010 cube steel, then you are at that region. Okay, now if your strain falls below that, right, you're not legal, you're not allowed to even design it. Let us say this is 0.002, so this is 0.25, so somewhere here let's say it is 0.004. That line is 0. Strain corresponding to strain in steel is 0.004. So only if your strain in the beam falls above to the right of this, okay, that means epsilon t greater than 0.00 greater than 0.004, that means you are in this region. Only then um, you are allowed to design and pick up your phi factor. Okay, as you can see, that region has so, so let's say this is 0.004, correct? So it can be within this region. Your strain can be from here to here, or your strain can be from in this region. So if your strain is greater than 0.005, pretty easy to, let's say here, here, or here, or here, it is very easy to pick up your phi factor. Then your phi factor is 0.9. But if your strain is less than 0.005 but greater than 0.004, right, within, then you are in a region called the transition region. Transition region is actually from here to here, but then since for a beam you are not allowed to have anything here, right? You're not allowed to have a beam there. So let's talk about the scenario only when your epsilon t is greater than or equal to 0.4. So if your strain falls here less than 0.005, greater than 0.004, then you have to go here and then interpolate. Okay, now how do you interpolate? There's an equation there, right? So this is the scenario wherein your strain is between 0.002 and 0.004 and 0.005. So that is in the transition region. Then If you have spiral, you use this particular spiral reinforcement, transverse reinforcement, then you use that equation to interpolate. If you have others not spiral reinforcement, then you use this equation to interpolate. We'll do all this in a problem. That's when your things will crystallize. But then for now, realize that this is a pretty important page. In an exam setting, you'll probably be coming here multiple times to this particular page. Correct. So there is a table for strength reduction factor based on the strain in steel, tension steel. You will either be in a compression controlled region, transition region, or a tension controlled region. For beams, you are only allowed to be in a region greater than wherein epsilon uh, T is greater than or equal to 0.004. Okay, anything 0.004 or greater. And then you will figure out if you're maybe you have a circular beam and then a spiral reinforcement as to your ties. Then if you're spiral, then you come here and find out, interpolate it, right? Find out your epsilon T. If otherwise you if you have hoops, regular beam, rectangular beam, reinforcement there, and you have regular ties, correct? Then you come here to this section and calculate your strain in steel value. Okay, I don't want to spend too much time here. We'll do a problem. That's when you'll realize. I mean, things will become. Maybe you already know all this, but then things will become a little more crystallized. So that is about this section. Let's see if there's something else important here. We'll go back to the beam section now. Beam was 135. 135. So we found out how we can calculate the phi value, right? So once the phi value is known, if we know the how to calculate the strength, nominal strength, then we are almost there. If phi value is known, if you know how to calculate your shear, then we are almost there. You compare those two things and we are almost there. Same thing for torsion and all that. Okay. Let's go back to where we were. So we'll see how the nominal capacity of a beam can be calculated and all that. What does the code say about, does the code give you any guideline of how to calculate? Okay, so I think I missed that part. Shear, torsion, okay, 1 second here. MU, MN. Factor torsion, the factored shear, factored moment. Let's start with factored moment. No, I want to do the nominal moment. I want to see where it tells us how we can calculate the nominal moment. Okay, here. Um, so how do you calculate your nominal moment? You will have to see, I mean, before you calculate your nominal moment, you want to see if you also have an axial force less than certain value or axial force greater than a certain value. Okay. So let's say you have an axial force less than a certain value calculated by this, then you calculate your nominal moment from this particular section here. So let's quickly go to the section and see what if there is any useful information. So nominal flexural strength, Mn, right? How do you calculate that? It says you have to go to this section. So this is where it will take you into loops. So now you have to go to 22.2, and if you go to 22.2, you will see that there are no equations to calculate your nominal strength. Okay. There are some assumptions. It is saying that the the strain in the extreme concrete compression fiber should not exceed 0.003, right? And any tensile strength of concrete in the tension zone should be neglected, ignored, right? So based on these assumptions, you will have to develop equations. We'll do that, but then these are the most important assumptions. Here it says the stress strain curve for concrete is like a rectangular parabola, meaning let's say you have a beam like that, let's say this is the neutral axis, right? And you are subjecting this beam to bending, correct? So you have beam UDL, it's trying to bend like that, correct? Then this side is under tension, that side is under compression, correct? And then the extreme fiber I mean, if I plot the stress strain stress diagram here, let's say here this is where the steel is. I plot a stress diagram. It will look like actual stress diagram will look like a rectangular rectangle and a parabola. Okay, and then there's nothing here. Then you have your stress in steel here. So that is how the stress strain diagram will look. But then because it is a non-linear, it'll make life tough in terms of calculations. So there is something called a Whitney stress block, which makes things easier, makes some assumptions, and makes the stress block a little more uniform. Not as deep as this one. We'll talk about all that. And this particular value is 0.85 times of FC prime. Um, and then using these assumptions, this one, that assumption, rectangular stress block, or an equivalent stress distribution here. Equivalent stress block is this one. So this part is talking about this stress distribution here, and this part is talking about an equivalent stress distribution, which is that one there. Okay, and that's why you see the 0.85 FC prime. So that based on that, you calculate your maybe this is the right time we talk about how the stress block and other things look. Okay, so let's do that here. Let's say you have a beam like that, right? You have a rectangular beam like that, right? You have reinforcement here, and then obviously this is has a neutral axis, right? So this particular zone here is subject neither to compression nor tension. Okay, now this is the geometry. Here is how the actual stress block looks, right? Stress in steel is pretty straightforward. AST, area of steel, times of yield strength of yield. You are assuming that steel has yielded, so times yield strength. That is your uh, tensile force. AST, area times stress. Now concrete, a little bit difficult because you have you have your rectangular parabolic stress diagram. So that is your rectangular parabolic stress diagram. The notation in the code for the depth of the neutral axis is not XU, it is C, right? Um, but then to make life easier, they have come up with a slightly different stress block, Whitney stress block, which is you would have learned all this in your undergraduate years. So that is the stress block. Here is the same tension, correct? And this is 0.85 times of FC prime. Correct. The only thing missing is strain now. So now you have to realize that this is not the depth of neutral axis. It is called A. Depth of neutral axis is C, and this is called A. That is the most important thing, and there is a relationship between um, your depth of neutral axis and A. If you know your A, then you can, if you know something called beta 1, we'll talk about it, then you will be in a position to calculate your depth of neutral axis. This is not a concrete technology class. I'll not get into uh, the equilibrium and how you calculate the moment, the lever arm business. I'm assuming you know all that. Okay, um, but this is good enough for an exam to solve problems and all that. Okay, so C, again, most important thing, C is the depth of the neutral axis. A is not the depth of neutral axis. Many times you will be calculating A and then back calculating your C. Okay, so now assume that this is the stress distribution. Then it's pretty easy to calculate your from the compression fiber to the tension fiber, this is your depth of the beam, right? Depth of this is small d. Capital D is from here to here, but that is not the D which is used in calculations. D used in the calculation is from the extreme compression fiber to the tension fiber. Now the last thing missing is your strain diagram. So if this is the neutral axis, strain diagram assumption is linear strains. So if this is the strain in concrete, then that is the strain in steel. So epsilon C strain in concrete, right? And that is limited to 0.003. Anything beyond 0.003, concrete will just crush. So we limit this value to 0.003 and then back calculate your strain in steel. How do you back calculate? Let us say you know this particular depth, which is C, right? Not A. This is C. Remember, this is A. Let us say you somehow calculated A and calculate, you know your beta 1 value, you found out your back calculated depth of neutral axis, then you just use, if that is C, then this is D minus C, right? Then you just use similar triangles. So C or epsilon concrete by C is equal to epsilon steel by D minus C. You know this as 0.003. You know this value, let us say it is 2.5 or let us say it is 5 inches. 5 inches. You know this value, if this is 5, you know the depth, so you know the D minus C, then you can, only unknown is epsilon T, and you can calculate the epsilon T. Okay. So once you know your depth of neutral axis and you know your A is the depth of the Whitney stress block, you know your FC prime, you know your Fy, you know your area of steel. Area of steel is just the area of the bars, right? Then how do you calculate your moment? All that you do is find your tension force, which is Fy times AST, correct? Fy times area of steel. So this is your force times some distance, your moment. Distance is lever arm distance from here to the center of that block, that compression block, which is D minus A by 2. Okay. So FST or Fy AST D minus A over 2 is your moment. This is your nominal moment, Mn. Okay. So nominal moment capacity of a beam is that much. So you take the nominal, we talked about the strength reduction factor. You take your strength reduction factor, multiply it with the nominal, then you get your mu. So that's how you calculate your mu value. Okay. So the only thing we did not cover here is how do you calculate your beta 1. Beta 1 is a function of the grade of concrete. It's right here, right? Beta 1 equivalent rectangular stress block related value. So your beta 1 depends upon your FC prime. FC prime is between these two. Beta 1 straightforward 0.85 and reduces for every 1000 psi increase in FC prime. So FC prime, for example, if it is a 5000 psi, then what you do is 0.85 minus 0.05 times your FC prime in the actual problem is 5000 minus 4000 divided by 1000. So that is 0.80. Okay. So your beta 1 will become 0.80. Now, how do you calculate the depth of the neutral axis? That is something we missed last time. So here is our beam, right? So that is your tensile reinforcement, and let's say that is the neutral axis, and here is the uh, strain diagram. It cuts there, right? And you have your Whitney stress block 0.85. This width is 0.85 FC prime. How do you calculate your depth of neutral axis? So the depth of neutral axis is pretty straightforward. You take your tension and equate it to the compression. Total tension, what is the total tension? Total tension is Fy stress into area of steel, right? What is the compression? The width of the block is 85 into FC prime. Where is it acting? It's acting here. What is the value? What is that area? The width of the beam is B. Area, depth of that value is A. So B times of A. In other words, A is FST or Fy times of AST by 0.85 times FC prime times of B. That is how you calculate A. That is not the depth of neutral axis. It's just the depth of Whitney block. Depth of neutral axis is this value here. You calculate C, you know your beta value. Earlier we calculated for a 5000 for FC prime is equal to 5000. Your beta was 0.8. So you take A divided by beta 1 value to calculate your C value. We'll do a detailed problem, but that's about this particular section here. Okay. Then we will go back to page number 135. Okay. At least we are in the beam section here. So that's how you calculate your nominal moment. Now we are talking about nominal shear, Vn. How do you calculate your shear capacity of a certain beam given a certain amount of reinforcement? Okay. So shear is not taken by this reinforcement. Shear is taken by this reinforcement is neglected. The shear is taken by concrete we call that VC. Portion of it is taken by concrete, and a portion of it is taken by the transverse reinforcement, which is that reinforcement. So VS. So in other words, VN has to be calculated from that chapter. We are not talking about composite, so we're not talking about this one. So let us see how VN can be calculated from that section there. So it's pretty interesting section. The good thing is it's very clear. You have a beam, you have reinforcement, and you have transverse reinforcement, right? When you apply shear, the shear is being taken by the total shear is V capacity is a contribution from concrete. Concrete will take a portion of it, and this transverse reinforcement that you are provided also takes a portion of it. So Vn is Vc plus Vs. Okay, but many times in the problem, you will be asked to calculate the design shear strength. That means you take the strength reduction factor, you take your nominal strength, reduce it, and that is your Vn. So it is phi times of Vc plus Vs. Okay, so that is pretty straightforward. Now, how do you calculate? Next question is, how do you calculate your Vc? How do you calculate that? Okay, again, very nice. I love this section because everything you need is here. The Vc value, you can go to this section, but Vc is calculated as 2 times lambda times root Fc prime times the breadth of your beam and the effective depth of your beam. So that is many times the case. I mean, it's pretty straightforward. You'll see these problems in the exam. Okay, you will be given a beam, and then there will be some reinforcement. Then you'll ask you the shear capacity. So you'll be wondering how to calculate your VC. The VC depends upon if you use lightweight aggregate, the tensile strength of the concrete. The strength of the concrete is dependent on all that. So there is a factor which reduces the strength if you are using lightweight aggregate and all that. But if you are using normal weight concrete, NCW, normal weight concrete, then your lambda is equal to 1.0. So most of the times this will be 1.0. So 2 lambda root Fc prime times, this is the stress, you times this is the area that will take the shear. So your area is that is your, the hatched portion is this area of this hatched portion here. Okay, so we calculate that. Remember this particular thing, we'll come back to that particular thing, but let's go ahead. Now, how do we calculate? So we figured out we figured out phi times of V nominal is what we want, because that is V ultimate. But V nominal is a portion of it is coming from concrete, portion of it is coming from steel, right? The portion of from concrete, straightforward. If you know your Fc prime, if you know the lambda, if you know your breadth of web, and if you know your depth of the beam, then you can calculate VC prime. Now, how do you calculate your VS? VS is also pretty. Before I go to VS, let us say if many times, sometimes you'll have a circular beam and your beam is subject to shear. Now we know that VC is a function of 2 lambda root Fc prime BW into D. We know BW is breadth of web and depth of beam. But if it is a circular beam, what is the BW? Okay, what is the T? So that is what is given here, right? Given here in this particular section, many times it is hidden. So we see solid circular D shall be permitted to be taken as 0.8 times the diameter. So D is nothing but 0.8 times your diameter, and PW is can be D. So circular shape, you know your D, you know your BW from this section here. Then you can calculate your, again calculate your, you're back in business, right? You can calculate your VC. Now, how do you calculate VS? I don't want to read all this text, right? That's not the purpose of this these sessions. These sessions is to notice what is important. Okay, before we talk about VS, so this is where that formula is. This is for VC, portion of the shear taken by concrete for a non-pre-stress member without axial force. That means your beam is not um, that means you have a beam like that, maybe with any boundary condition, but there is no one pressing these things in this direction. There is only load which is causing shear, right? But there is no axial load. So this is the axial. Whenever there's axial, is along the length of the beam. So when there is no axial, then pretty straightforward. You know the breadth of the beam web, depth of the beam. You know your Fc prime. You find out you know your lambda. Then you can calculate Vc from here. Okay. Now what happens, I mean, this is a simplified method and there is also a detailed method. So a detailed method, you will calculate your VC from these three and you'll take the least of those. Okay. Detailed method involves something called MU by VD by MU. So this ratio will be found in the detailed method. So in the detailed method, you need to know what your shear force is. Ultimate VU is, you need to know the depth of the beam. You need to know what your ultimate moment capacity of the beam is. Sorry, factored moment is. Factored moment, factored shear. Sorry. This is VU D by MU. So this is a factored moment, factored shear. If you know that, you plug it here again. Again, it's pretty simple. It's something like um, this whole thing is the stress, and that is the area here. Correct. So this is area. Oops. So that is the area, and this is the stress. Sigma times area is your force. That's the force. This is capital VC, so that is a force. Sometimes you'll also see small VC in other sections. That is, this is stress, whereas if you have capital VC, that is a force. Okay. So that is about VC when you don't have an axial force. What happens if you have an axial force? VC members with axial compression. So you have a beam and someone is pressing the beam, and there is also load on the top. Now the shear capacity increases a little bit. So what is the axial load? If you know the axial load um, the gross area of the section, you know BW, you know D. So again, this particular portion here is nothing but your stress. This is like your sigma, that is your area. Stress times area is equal to your force. Stress times area is force. That's the business there. Okay. There is again a detailed procedure, similar, same thing. You see your VU, MU, NU getting involved in this particular thing, but then you calculate that, you calculate this, pick up the lesser of these two. Okay, so nothing important about that. Now, when you have significant axial tension, what happens if you have a beam but it is being pulled, right? And then that's supported like that. Okay, so the load is causing shear. The shear is getting affected by your tension NU. So when you have tension, first thing important is this one. NU is negative for tension. Let's say they say in the problem statement says 200 kips tension, then you have to treat this NU as a minus 200 and use it in the formula. Okay, 200 kips, so 200 into 1000 pounds if you are using this in PSI. Okay, so nothing fancy about that. When you have tension, how do you calculate your VC? Again, we are calculating the portion of the shear that concrete itself can handle. Okay, so pre-stress, we are not getting into all these details, but there are straightforward equation for if you have pre-stressed beam, how do you calculate your values? Okay, let's see if there is anything else important. Otherwise, we'll go back to our beam business. Okay, so this is the thing I was looking for. Now you have so like I said, Vn nominal is Vc plus Vs. We know how to calculate our Vc. Usually it is 2 root Fc prime Bw into D. How do you calculate your Vs? Vs is nothing but Vs. I mean, if you rearrange this equation, phi times of Vu, sorry, Vn is equal to phi times of Vc plus Vs. So this is nothing but Vu. Vu is equal to phi times of Vc plus Vs, correct? Vu by phi. So Vu by phi is nothing but Vc plus Vs, correct? If you know Vu is always given, Vu by phi minus Vc, then you will get your Vs. So that's how you calculate your Vs, and that is what is given here. Okay. And this is like I said, the Vs component is being resisted by, you have a beam and you have your transverse reinforcement, right? And this is transverse reinforcement here. The shear Vs component is based on the area of that reinforcement. So if you have, let us say you have a number 3 diameter bar, then the area of shear reinforcement is called, the notation is AV in the code, is nothing but two sections are resisting your shear. The shear being applied is being resisted by two sections. So you take 2 times you got pi, number 3 is 3 by 8 inch diameter, right, square by 4. So that is your area of shear reinforcement, right? So you calculate your AV, you multiply it with the Fy of the shear reinforcement, um, right? And then d by s is nothing but s is the spacing of the shear reinforcement, d by s is the number of bars. Um, so this is how you calculate your Vs. Okay, right? So Vs is here. So we talked about how we can calculate Vs. We talked about how we can calculate Vc. We talked about strength reduction factors, and that is your ultimate shear capacity. If this is more than the ultimate, we are good. If this portion here is less than the ultimate shear capacity, then we have to redesign. Okay. One catch here is, let us say, I mean, there is an upper limit to your Vs value. The Vs value cannot be, I mean, should be less than or equal to 8 times lambda root Fc prime into Bw into D. Okay, so that is very important detail which is given at the very start here. Okay, so your Vc value has to be calculated as 2 lambda, right? So Vu should be less than phi times of Vc. Vc you know how to calculate, but the upper limit is 8 for Vc is 8 FCW Bw into D. Okay. So if your Vs value that you calculate is less than this particular upper limit, then you use that. Okay. So let's say the upper limit is 200 kips. Okay. Whereas the Vs that you calculated is only 60 kips or 160 kips, then you use 160 in your equation. If you whereas the Vs calculated is 210 kips, then you only use 200. Okay, that's the upper limit. So Vu has an upper limit. Sorry, Vs has an upper limit. So you need to realize and be careful with that particular thing. Okay. So we talked about shear. How do you calculate your Vc and Vs? Now let's see if we can find out how we can calculate if there is a need for a minimum shear reinforcement and all that. Okay. Let's see. I'll keep going here. I think we covered this in the two-way slab chapter, right? This is another important chapter. We did cover this in two-way slab, but then this is where you see a small VC. Small VC means you only have a stress. You don't have your area term here. Okay. And let us say you have a column. There is a column. There's a column, right? There's a column, column, and there's a slab. Okay. So for this particular column, um, the two-way shear happens. We talked about it detailed in other sections. It happens in a region which is d by 2. The distance between these two things is d by 2 from the face of the support, and the perimeter of that critical perimeter of this line here is B naught. Okay. So if you know your parameter B naught or perimeter, and you know your alpha value, and so this particular table, you need Fc prime, you need lambda, you need your beta value, which is based on the size of your column, right? 18 by 18 square column, if beta value is 1, rectangular column, you calculate beta for this particular thing, and then you can calculate, and then you need your the B naught, the critical perimeter that I was talking about. Once you know the critical perimeter, we'll do a problem on this, so don't worry if you don't understand. Once you know the critical perimeter, then you calculate this, that, and pick up your shear stress as the least of these three. Okay. What do you do with the shear stress? You multiply it with the area, find out your shear strength. What do you do with the shear strength? Compare it with the load, and if the strength is greater than the load coming, then we are good, right? Let's see. There is another. I thought there was some detail. Okay, let's go back to our beam uh, and see if there is anything important. Uh, I mean, for a breadth level, for depth, every little detail here is important. But then, just for a breadth level, P or okay. So this is minimum shear reinforcement, right? So whether you need it or not in a beam, you need to provide a minimum amount of shear reinforcement, right? Shear reinforcement is that particular stirrup there, and um, if your if your VU that is coming is if your VU, which is the factored shear that is coming on the beam, is between sorry, if it is less than half of VC, right? Then you don't need to provide any shear reinforcement. Okay, but if your VU is greater than half of VC, so factored moment, let us say 70, um, and half of VC is equal to, let's say, 150, um, uh, and so half of VC, this VC is 150, so zero point 0.5 times VC is equal to 75. Now VU is less than half of VC, correct? In this scenario, uh, uh, you don't have to provide any uh, minimum shear reinforcement. AV minimum shall be provided in the regions where VU is greater than half of VC, except so you have to do always except you meet these conditions, except when you have a shallow beam, when you have an integral web slab meeting this condition, and when you have a certain condition, right? So that's about AV minimum. And now let's get into, this is the most important thing, AV minimum. How do you calculate the minimum shear reinforcement that is required, right? So we are not talking about pre-stress. So forget about this part. Forget about this part because this is dedicatedly for pre-stress. This is pre-stress with some certain condition. We're talking about non-pre-stressed beam. Then it is a greater of your AV minimum by S. It's not just AV minimum. The table says AV minimum, but what they give you is AV minimum, AV min divided by S. S is the spacing of the transverse reinforcement normal to the screen, right? So that's the transverse reinforcement. This is the main reinforcement. The S is the spacing. Many times you will see number 3 bars or number 4 at 6-inch spacing, something like that. Okay, so that is your S value in this particular case. So your minimum shear reinforcement, AV minimum, is the greater of that and that. And all that you need is again FC prime, BW, FY. Most of the times you know all that. You can calculate your minimum. This is about torsion. We're not doing torsion today, right? And cover related information is here. Development length related information is here. Splice length related information is there. Correct. Bundle bars and all other things are here. What we are looking for is the spacing of the shear reinforcement, right? For the spacing, I think there is a table somewhere here. Let's see if it is here. Okay, so this is all. So now maximum spacing. Many times in problems, what happens is you calculate based on the loads given and dimensions given. You calculate and the factored shear that is given. You calculate and you find out your spacing is like 15 inches shear reinforcement spacing. But you have to. I mean, there will be an answer related to 15 inches, but there will also be an answer saying that it is 6 or 7 inches, right? So you must be very careful. You need to understand this particular table here. Maximum shear spacing allowed depends upon your Vs and this particular value. If your Vs value is less than 4 times root Fc prime Bw into Dw, then you get into here. You find out for a non-pre-stressed beam. We are not talking about this today. Non-pre-stressed beam, it is the lesser of d by 2 and 24. Okay, but if that Vs, you know Vs now, right? Nominal concrete portion of it is taken by concrete, the portion taken by the steel. The portion taken by the steel is greater than this particular factor, right? So Vs greater than 4 root Fc prime Bw into dW, then you fall under this in this row, and then you pick up your value from d by 2 or 12. So that is the minimum spacing required, so maximum spacing required. This will ensure that you will have a bar in the where a crack happens, right? Every crack is covered by at least one bar. Okay, so that's all I have. Let us do a couple of problems and then we can continue this one. Okay, so let's talk about this particular problem here. Theory is one part, problems are problem is what makes you right. So let's see what we have here. So problem says RCC beam shown in the figure. I'll draw the picture for you. But then it is asking for the flexural strength in kip feet. It's giving you the breadth, the area of steel, the FC prime, Fy, and the zero axial load. So here is the beam, correct? And there is steel reinforcement here, right? Um, capital D is 18. Most of the times you're not worried about that. We want your small d. So capital D minus the minus this particular clear cover, and then they have the diameter of the bar. That will get you to this level. So small d is equal to 16 inches. The breadth of the beam here is 12 inches, right? And we are FC prime is 3200, Fy is 6010 cube. We are asked to calculate the capacity of the beam. Okay. So first thing we do is calculate the area of steel. AST is nothing but how many bars do we have? 4 bars. What is the diameter of the bar? 4 number 8 bars. So 4 into pi into 8 by 8 square by 4. Okay. 4, 4, 8, 8. That means this is lucky number. So that is the area of steel. Okay. So we have our area of steel. Once our area of steel is given, you like I said, here is the actual stress block, rectangular parabola. That means that is the neutral axis, that actual strain, right? So the epsilon. So this value here, epsilon concrete should not be greater than 0.003, right? Whitney stress block to make our life a little bit easier, correct? And this value here is 0.85 FC prime, correct? And this is A, and this is C. C is the depth of neutral axis, A is the depth of Whitney block. Okay. Now how do you calculate your A? AST into Fy divided by 0.85 Fc prime into B into dW, right? AST 3.1415, Fy 6010 cube, 0.85, Fc prime is 3200 times your B, right? With the 12 times of what is your dW, 16 effective depth. So when you calculate that, you end up with 5.77 inches. Okay, so that is your A. It is not the depth of the neutral axis. To depth of the neutral axis is A by beta, right? And the beta is as we talked about it, beta 1 is a function of your Fc prime. Fc prime is 3200 is your Fc prime in this problem. So you need to calculate your beta value um, from the table that I showed you. But then Fc prime, because it is 3200, your beta 1 is 0.85. Okay, so C is A by beta 1, which is your 5.77 inches, by your beta 1 is 0.85, roughly 6.794 inches right there. Okay, so now that you have your depth of neutral axis, we can visualize what is happening here. So depth of neutral is only 6.74, so that means we have a 14 inches deep beam. 16, right? So from here to here is 16 inches, but my depth of neutral axis is not 8, not in the middle, somewhere slightly above. So let's call it, let's say this is the neutral axis. Now you calculate your, this is your 0.003, right, at failure. And then you need to calculate your epsilon uh, steel, strain in steel. Okay, so the strain in steel, pretty straightforward. Um, what you do is your 0.00, use similar triangles, 0.003, but that distance here is 6.79, correct? You use that one, and d minus 6.79 is 9.2 something. Okay, so 003 by your 6.79 is equal to epsilon t by your 9.2 with that depth there. Okay, that gives you your epsilon t as 0.0406 or something like that. One thing to notice is this one is greater than 0.004. That means this is the legal beam. Okay, but it is not close to, I mean, your epsilon s is between 0.004 and 0.005. Okay, so we are not done yet. We still have to calculate our phi factor. Correct? Remember, the phi factor is a curve like that. Epsilon steel. This is your phi, right? And it was something like this and something like that, and then it became like that. Correct? You are somewhere in this region because this is where epsilon t is close to 0.0406. So we have to interpolate, right? And to interpolate, we use that. I showed you the interpolation formula, 0.65 plus 0.25 times the actual strain in steel that you are seeing is in this problem is 0.6 minus 0.002 divided by 0.005 minus 0.002. Okay, so that will result in 0.822 as your phi. Okay, so now you know your phi, and you then you must be in a position to calculate phi times of mn. So phi times of mn is nothing but 0.822 phi mn. Mn is the FST times of area of steel times the lever arm d minus a by 2. Okay, so that is 0.822 FST 60 into 10 cube, area lucky number times depth is 16, a was 5.77. So this is where people do a mistake. This is a, not depth of neutral axis now, and that will be close to 169.35 kip feet. Okay, so we calculated our feet times of mn as 169.35 kip feet. Okay, a lot of calculation to do, but then once you read the question and you find out your area of steel and you start drawing all these sketches, the most important thing would be to calculate your beta and then not mix your C value with your A value. A value is not the depth of the neutral axis. This is based on your compression and tension, right? You equate the compression to tension and calculate your A value, and from the A value divided by beta you calculate your C value. From the C value, you use similar the properties of similar triangle to calculate your strain in bottom fiber. Once you know the straining bottom fiber, now you know you have a nice curve, strain in bottom fiber versus phi factor. Only thing you need to check is your beam should be a legal beam, right? So strain should be greater than 0.004. Uh, that will ensure that steel has yielded and all that. Much beyond the yield. Yield is 0.002, but we want it to be well into the yield zone. Okay. Once you find out that it is legal, then you do this interpolation to calculate your actual value. If you were to be if your strain in the steel were to be 0.006, then we are greater than 0.005, and we could have easily used a phi factor of 0.9. But then the strain is between these two values, so you come here and interpolate. Once you do that interpolation, then it's a nominal moment again one last time. you take a phi factor, and you take your area of steel times of FST times your D minus A by 2. This is lever arm. This is the force. That is the moment capacity from the tension side. Okay. All right. So that's the first problem. I want to, let's see if we can do another problem here. Okay, so let's say this is the next problem. Maybe we'll stop after this problem, continue it. Okay, so that is your problem description. RCC beam. Um, there's no picture. I'll draw a picture for you, but then uh, so the idea is to calculate given an RCC beam, and it has compression and tension reinforcement. How do you determine determine the phi value, that is the strength reduction? They're not asking you for MN or anything. They're just asking you the phi values and basic information like what is the compression reinforcement, what is the tension reinforcement, what is the FC prime of concrete and steel. All these things have been given. Okay, so here is the beam, right? Breadth is given as 9. Effective depth, so it is compression, is tension steel, and there is also I'm just drawing it as a block. You know, the beam will have reinforcement circles there. Okay, I'm not drawing all that. So this is AS prime, which is 4 times of number 7 bars. So you take mm, number 7 bar is 0.6 inches, and you multiply with 4, you get 2.4. Okay, so this is AS, and that is 4 bars of number 9. Number 9 bar, you must be a little careful. Area, the diameter of number 9 is not 9 by 8. You'll have to go to the table in your PE handbook and then pick it up. Okay, but then the area of number 9 is 1.0. So let's handle the area part. So because we know there are 4, and each number 9 bar is 1 inch square, so you have 4 inches square as your AST. Okay, now if you look at your PE handbook here and go to the concrete section, let's go to the top. Again, you could have used bookmarks. Concrete. Okay, works. So this is where you get your area information from, right? From this table. Number, like I said, number 9 bar is not 1 inch. It is 1 point something. Area is 1 inch. Okay. What I want to show you is there is a section wherein they show you how to calculate this one here. Okay. So this is for your for the previous problem where we did all this, correct? And this is your A. A is not the depth of neutral axis. A is the depth of Whitney block. Okay. The Whitney block will be something like that. Stress 0.85 FC prime. Okay. Anyway, so what we want to cover now is this particular thing. This is the scenario we have now. We have some AS. We also have some reinforcement on the compression side. Okay. When that happens, you need to use this equation. Okay. So your A value is AS minus AS prime into Fy by 0.85 FC prime times of P. Okay. Going back here, we'll use that formula to calculate our AS. So the depth of Whitney block is nothing but AS minus AS prime times of Fy by 0.85 times of FC prime times of B, BW. So that is nothing but 4 minus 2.4, correct? This is 4, this is 2.4 inch square times of 60, 10 cube, 0.85, 5000 is your FC prime into your B. So the A value ends up to be 2.51 inches. Okay. So once you know your A, based on your FC prime, you can find out your beta value. Beta value, like I said, is a function of your FC prime value. When FC prime is 5000, beta becomes you can calculate this. Beta is just 0.85 minus 0.05 times of your 5000 minus 1000 divided by 4,000. Sorry, 1,000. 5,000 minus 4,000 by 1,000. So that is 0.85 minus this is whole thing is 1, 0.05. So this is 0.8. So once you calculate your beta, then you come to C. C is A by beta, 2.51 inches by your beta is 0.8. That is, you get your CS 3.14 inches. So if you think about it, the beam is from here to here is 16 inches, but your depth of neutral axis is somewhere there, right? That means if I draw the beam again here, that should hint about something. So that is telling us that here is my depth of neutral axis. So for a small strain in steel, even if it is 0.003, you might end up seeing decent strain in your steel. Okay, so I want to calculate the strain in steel, and that would be using similar triangles again. So from here to here, that value is 3.14. So 0.003 by 3.14 is equal to epsilon t by this distance from here to here. That is your d minus 3.14. Okay, that value will be so d minus, yes, d is your 16 minus 3.14. You can calculate epsilon t. Epsilon t is 0.0122, which is way greater than 0.005. That means we are well beyond the tension steel is yielding. Okay, that's not the end of it. You need to come back here and calculate the strain in your compression steel. Somewhere here you also have your compression steel, and that formula that we used for A calculation, which is this one, you are assuming that the steel has yielded in compression. The tension steel has yielded, and also the compression steel has yielded. So we have to come back and check that. So to check that, you need one piece of crucial information, which is how far is your compression steel from the edge. I think I didn't show that to you in the problem definition, but then that was somewhere close to uh, let's see here, that is from, I think that is 2 inches from the center to here. This is 2 inches. Okay, so here is our neutral axis. Neutral axis, we found out that is C, that is at a distance of 3.14. So 3.14 here. So this value here from here to here will be 3.14 minus the 2, 1.14, and this is epsilon s 0.003, epsilon t 0. Question mark. Sorry, we are finding the epsilon here. Epsilon in our strain in our compression reinforcement is equal to question mark. Okay, so similar triangles again, 0.003 by that distance 3.14 equal to epsilon c prime or whatever divided by that distance 1.14, and when you calculate your epsilon prime in compression steel, that would result in so you will, I mean, that value will be 0.00108, right, when you do this calculation. So that is much less than 0.002. So that means the compression steel here has not yielded. So that since the compression steel has not yielded, that means the stress in the compression Fs prime, stress in compression steel is just strain in compression steel. Let's call it S. Okay, S prime, S prime epsilon S prime divided by your Young's modulus. So you take that value 0.00108 divided by 29 into 10 power 6. You get your stress in steel as 31.58 KSI. So this is way less than, notice that this is less than 16 to 10 cube. because the compression steel has not yielded. Now, but the formula that we used assumed for calculating A assumed that your compression steel has yielded. You have to come here and recalculate your, this is the most important step and tricky part in the equation. So you now you recalculate is AS into Fy, right? Whereas AS prime into Fs prime, right? Divided by 0.85 Fc prime times of P. So that is 4 times your 6010 cube minus 2.4 is the area of compression reinforcement times 3. Sorry 30 31 31 is your stress 31.15 into 10 cube, right? So that is the thing divided by 0.85 times of 5000 Fc prime times of P. This is 4.293 inches. Okay. So now the neutral axis, we recomputed the depth of Whitney stress block. We recompute the depth of the neutral axis as A by beta. Beta 1 will not change. This is the new A divided by your beta. That is your new depth of neutral axis. Okay. Since there's a new depth of neutral axis, we just check to see, double check to see what happens to our strain in tension steel. So tension steel, new depth of neutral axis 5.36, right? So your strain diagram, cut at neutral axis 0.003. What is this one here? Epsilon s. So 0.003 divided by 5.36 equal to, what is this value? 10.63. How do you get it? D minus that. So epsilon s, strain in steel, tension steel, by 10.6. So you calculate your epsilon s 0.056. This is well over 0.004. That means it is legal. It is also greater than 0.005. That means we are in the flat region there, somewhere here, right? Somewhere here. This is your strength reduction factor. This is your epsilon c, s, or t, what strain in tension steel. That means our strength reduction factor, if you look at the picture, this is 0.9. That means we can use a phi factor of 0.9 for this problem. Okay, such a simple question, but pretty conceptual, because the inherent assumption in using this formula here is that the compression steel, and the tension steel have both yielded, right? So this and that have yielded, but so we assume that they have yielded. Find out the depth of Whitney's block, then find out based on the beta value, which is a function of Fc prime. You calculate your depth of neutral axis, that is this much. Then you plot it, use the principle of similar triangles, calculate your based on the fact that this cannot go beyond 0.003, and you use the properties of basic geometry and find out your strain in tension steel here. You find out strain in tension steel, that shows that it is much greater than 0.005. So you think you are good, right? Because you want your steel to be, tension steel to be far in the yield zone there. Now, but you come here and calculate what happened, the story of your compression steel. What is the strain in compression steel? This distance is 2. Again, you find out your similar triangles. You find out you know this, you know that depth, you have to find out that, and you know that depth, right? So from similar triangles you find out epsilon c as that value here, which is much less than 0.002. This is the yield strain. What is 0.002? You have a 60 into 10 cube steel by the Young's modulus of concrete, then steel, that is 0.002. That is the yield strain, but this is less than the yield strain. That means the compression steel has not yielded. That means you need to recompute your depth of Whitney stress block, A value here. You recompute that and you find out your A value is 4.293 inches, way better than last time. It was 2.56 or something. You calculate your C value. This is the depth of the neutral axis as A by beta. Beta will remain same. You calculate that and you use that particular depth of neutral axis. Use similar triangles again to calculate your epsilon S value. which is strain here. Okay, so now you calculate the strain in steel greater than you find out that it is 0.056 greater than 004. That means the beam is legal. Greater than 005, that means you are in the flat plateau area. Life is easier. Your value, this value here is 0.0056. You are in that region. So you come here and pick up your phi value as 0.09. Okay. If I want to do some more interesting problems, those problems will be on flexure and shear capacities. But this is what we did for today. We're running out of time, so um, we'll do some nice problems uh, in the next video, and they will be related to calculating the shear capacity of a beam and moment capacity of a column, and you're calculating the flexural capacity of a column that is subject to not only bending moment but also axial forces. Right? Thank you.